Welcome to 78th lecture. We are studying transient analysis, and in this lecture, we will continue studying the circuit that we started studying in last lecture 77. Right. In the last lecture in CA77, we took on this circuit where the switch had been in position 1. This is switch K. It had been in position 1 for a very long time, and then unless it achieved steady state, and then it was moved to position 2. Right. Right. When it achieved steady state by being in position 1, this means that this capacitor would have been open circuited and there would be no current in this path, and the whole V, the applied voltage, the applied DC voltage, would have been appeared across this capacitor. And when the switch was moved to position 2, this charged capacitor worked like a temporary voltage source to cause a current flow through this resistor R2 for some time. Right. And we computed an expression for this current I2 of t that this charged capacitor caused through this circuit when the switch was moved to position 2 for all t. Initially it is V over R, and then as time approaches infinity, I sub 2 of t would become 0. Right, so capacitor was initially charged at voltage V when the switch was moved to position 2. So the capacitor was then charged at a voltage equal to the supply voltage V when the switch was moved to this position number 2. At that time, the capacitor was charged at voltage V. So what we are required to find now in this lecture, in last lecture, we computed I sub 2 of t, the current flowing through this resistor R2 or R. So in this lecture, we'll find the voltage drop as a function of t, as a function of time across this capacitor. So how would we do that? For that, V sub c of t, we know this is the integral based formula to compute V sub c of t across this capacitor. 1 over c integral of the current flowing through it. And fortunately, we know the expression for the current flowing through this capacitor, because after it has been moved to position 2, there is only one current in the circuit because there is only one loop. But this integral is from minus infinity to t to cater for any voltage that is already available across this capacitor, like we have in this case. When it was moved to position 2, we have a voltage drop across capacitor. So if the capacitor is pre-charged, this integral from minus infinity to t takes care of it. And we have already studied that this integral can be broken down into minus infinity to 0 and then from 0 to t. And this includes the effect of pre-charge if the capacitor is pre-charged. So in this case, the capacitor is pre-charged at a voltage V. In fact, the capacitor is charged at a voltage minus V, because when we apply KVL to this circuit, we assumed I2 of t to be flowing clockwise. And the clockwise flowing I2 would cause a voltage drop across capacitor in this polarity. But the applied voltage the voltage that is already available across capacitor is in the opposite direction. Therefore, we should put a minus with the capital V. right? So because this is in opposite polarity, therefore we put a minus here. So minus V is the pre-charge voltage across. It's an already available voltage across capacitor. So capacitor is pre-charged at voltage V, in fact at minus V, plus this integral. Let's put the value of I2 of t that we computed in our last lecture, V over R e to the minus t over R C. So now we have this expression V over R. It should come out of integral because it's not function of time. And then we have to integrate this. This is a simple exponent that we should integrate. And this RC cancels with this RC. And when we put the limits, e to the minus 0 becomes a 1. So multiplying this V inside this gives us minus V to the minus t over RC plus minus into minus plus V. So we have this minus V and this plus V. So they cancel. So they cancel each other. And we are left with this expression. There's a minus missing here. There's a minus sign missing here. So initially it is charged at minus V volts. And it is initially charged at minus V volts. This is minus V. And as the time goes on, this reaches 0. So initially it is minus V. This is a wrong plot. In fact, this is the plot. This is minus V as the time is 0, and then it starts increasing itself unless it becomes almost 0, and then it is exactly equal to 0 as time is infinity. So this is the right plot for V sub C of t. Right. So it's a decreasing exponential, not necessarily. In fact, it is an increasing exponential because the magnitude increases, but it settles down itself at a value that is almost 0 and becomes exactly equal to 0 as VC approaches infinity. Right, that's all for this lecture. In our next lecture, we'll use MS Excel, Microsoft Excel tool, to draw these exponential plots that we usually get while we analyze these transient circuits. And that will be interesting. Thank you.